So one thing that Descartes came up with is his rule of signs, and it says as follows: the number of positive real, so let's think about what that includes. Does positive real include imaginary? No. Does positive real include the square root of 2? Yes, square root of 2 is a real number, it's positive. Does positive real include 5? Does it include 9/4? Yes, it just doesn't include imaginary numbers. And then the number of negative real would just be negative. And it's equal to the number of sign changes in p of x or less by a factor of 2. And the number of negative real roots is equal to the number of sign changes in p of negative x or less by a factor of 2. And so this helps us make a good guess. Again, we want to make intelligent guesses when we're trying to look for roots of polynomials and be able to solve them. And so here we have p of x. And I'm going to identify the number of positive real solutions. Okay? So you look at the coefficients. Is the first coefficient positive or negative? It's positive. It's positive 3, correct? Does it stay positive when you move to the next one, or does it change to negative? It changes. So therefore, you can see here that there is one sign change. Now, it goes from negative, and it switches to positive. That's another sign change. And then it goes from positive to negative. So you can see of the 4 coefficients, there are a total of 3 sign changes. Therefore, there are 3 positive real roots. Or there might not be 3. So you're going to be 3 or less by a factor of 2. So 3 or 1. And here's why. Basically, what it's telling us is the graph either goes like this, where it crosses 3 times on the positive side, or it looks like this. If it looks like this, there's 1 solution. If it looks like this, there are 3. Now, if it looks like this, there's 1 real, how many imaginary would there be? 2 imaginary. Imaginary always come in pairs. They always come in pairs. So there's either 2 or 4 or 6, depending on the situation. Okay, so you can see that in that situation we have 3 or 1 positive real. Let's look at this one. Is there a sign change from negative x to the 4th to negative x squared? Is there a sign change from negative x squared to negative 1? So therefore, there are 0 positive real roots. There are none. So if I was using the rational root theorem, would be a good idea to guess 1? No, it wouldn't. There are no positive real roots at all. Okay, we look at the next part. The number of negative real roots, I have to first find not p of x, but p of negative x. What does it mean to find p of negative x? Well, I get negative x for x. So p of negative x is equal to 3 times negative x to the 3rd minus 4 times negative x squared plus 5 times negative x minus 2. Negative x to the 3rd. So I get negative 3x to the 3rd. Negative x squared is x squared times negative 4 is negative 4x squared. 5 times negative x is 5x minus 2. Okay. How many sign changes are there here? None. So there are no negative real roots. So it would not be a good idea to try plugging in any negative numbers. Okay. Let's do this one, p of negative x. What is negative x to the 4th going to come out to be? Negative x to the 4th. Negative x squared? It's the same, isn't it? So how many negative real roots are there? There are none. Before we take out our calculators and validate that, I just want you to show you something. Would you agree that all these exponents are even? So when you do p of negative x, the sign doesn't change for even exponents, does it? Look at this one. Did the sign change for the even exponents? Did it change for the odds? Yeah, so you can maybe do it a little bit more quickly by just changing all the odd exponents and leaving the even ones alone. So take out your calculators, plug these in. I'm plugging in the first graph. That's a cubic. Does it cross on the positive side or the negative side? Positive side. Does that make sense? Because it said we're either going to have 3 or 1 real roots. Does it cross at all on the negative side? And we said you're not going to have any negative real roots. How many times does it cross? Once or 3 times? Once. So therefore it has 1 real and it will have 2 imaginary. Okay? Let's look at the other one. If we go into y equals and we type in negative x to the fourth minus x squared minus 1, does that ever go above the x-axis? Never. So it has 0 positive real, it has 0 negative real. And so it's neat that just by looking at the equation, we can already determine some behavior about the graph. That's going to help us as we move forward. Okay? All right. Flip it over. We're going to do just a short little bit here. All we're going to cover is just this example 2 and 3, and then we're going to be done for the day. But the idea is regarding this upper and lower bound piece. People often get confused with this. And I just want to remind you that yesterday we looked at a polynomial like this, um, where the last coefficient or last number was 48, right? There's a lot of choices, aren't there? Like we listed them all off. Wouldn't it be nice if you knew not to plug certain ones in? I mean, do you mind trying to plug in 1 to that? It's not that big of a deal. But would you mind trying to do 48, especially without your calculator? That would be a bad deal, wouldn't it? So here's the deal. 48, 24, 16, da 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 da, 1, 0, negative 1, negative 16, negative 24, negative 48. What we can do with this next piece is we can determine upper and lower bounds. And you're not going to do this a lot. I'm simply just going to show it to you. You're going to have a question on your test like it, but I will refer every once in a while to it in class. And the idea is this. If we can find out that 5 is an upper bound, meaning there are no solutions greater than 5, which ones could you cross off? Yeah, you could cross off everything up there, right? And if you found out that negative 1 was a lower bound, which ones could you cross off? Everything else, right? And so therefore, we would only plug in numbers that are between those values. That would be good information to know. Agreed? So here's how it works out. Here's how we can tell if things are upper or lower bounds. If b is positive, it might be an upper bound. If, when you put it through the synthetic division, you have these coefficients up here. If all of your answers are non-negative, so all of your resulting coefficients, if they're non-negative, meaning they could be positive or they could be 0. So this is the question that would be asked on the test, and it's really a very straightforward question. It'll be something like this. show that this polynomial has real roots that lie between -3 and 2. So that means one is an upper bound and one would be a lower bound. Tell me which one would be an upper bound, -3 or 2? Yeah, so 2 is the upper bound. So what I will do to show that it's an upper bound is I will run it through synthetic division. And so I list 1, 0, -3, 2, -5. 2 times 1 is 2, 4, 2, 8, 3. What do you notice about all of my resulting coefficients? They're all positive because all coefficients will prime. Because all coefficients are that was great. Next time, let me know. I'll bring a mic back there. Okay. All right. Because all the coefficients are non-negative, 2 is an upper bound. Not too difficult to do, right? Suppose A is negative. A might be a lower bound if, when you run it through synthetic division, you come up with alternating signs, and 0 counts as an alternating sign. So say you get positive, 0, positive, negative, 0, negative, positive. That would count as alternating signs. One more time. Oh, the remainder doesn't necessarily have to be positive. Just needs to continue in the alternating fashion. Yes, or 0. Well, no, if it was 0, then that would be well, yeah, that would be actually a solution. So that would still count. Okay, so it could be 0. It could be 0. All right. So in this problem, the lower bound would be -3. So I plug in -3. I run it through and I get 1, -3, -3, 9, 6. And what do you notice about my coefficients as a result? Yep. Not a big deal, huh? Okay, let's put it all together. Find all rational zeros of the polynomial and then find the irrational zeros, if any. Whenever appropriate, use the rational roots theorem, the upper and lower bounds theorem, Descartes' rule of signs, the quadratic formula, or other factoring techniques, and if able, sketch a graph. So this is kind of a culmination of everything we've done so far. And tomorrow, or I'm sorry, not tomorrow, but Thursday, we're going to extend that even more to kind of a larger idea and larger problem. Okay, so let's see what we get. First of all, what's the degree? 3. So therefore, I'll have 3 solutions. They will either be a combination, or they'll either be all real, or they'll be real and imaginary. Now, we'll talk more about imaginary solutions on uh, Thursday. But right now, we have 3. And so we're going to look for the positive real. And I do that by looking for the number of sign changes. How many sign changes do you see? 2. So there's either 2 positive real or 0. So less by a factor of 2. I then have negative real. Well, I have to do p of negative x. And as we talked before, the sign will change for the odd exponents and stay the same for even exponents. So p of negative x will be negative x to the third minus 3x squared plus 13x plus 15. So the exponent is even, so it stays the same. How many sign changes there? 1. Now you can't subtract 2 and go down to negative 1. So we're guaranteed there's one negative real. This for sure crosses on the negative side of the x-axis. It must. Okay. So my p's and q's and choices. What are my p's? 1, 3, 5. And what are my q's? 1. So my choices for my rational roots are plus or minus 1, plus or minus 3, plus or minus 5, and plus or minus 15. Now, it looks like there's 2 positive, maybe 0, but there's for sure 1 negative real root. So would it be reasonable to try negative 1 or negative 3? Yeah. I think it's always just best to start with 1 and then go from there. So let's try 1. You plug in 1, you get 1. We're not doing that one. Minus 3, minus 13, plus 15. Does that work out? Yeah, so 1 works, so therefore x minus 1 is a factor. So we're going to divide 1 into the polynomial, and I get 1, negative 3, negative 13, 15. Drop the 1, multiply. So it does factor. That's what it factors to. Does the x squared minus 2x minus 15 factor? To what? Yeah. So therefore, our solutions are what? 1, 5, negative 3. So let's compare that to our original work. Did we find 3 solutions? Yes. How many did we find? 2 positive real or 0 real? We found 2 positive real. Did we find one that was negative? Yes, we were guaranteed that we would come up with one negative. So you can see it's a nice way to kind of even check your work, right? But we're going to add on to this on Thursday with complex solutions. The last thing we need to do is be able to sketch the graph. This is third degree. It's positive, so it ends which direction? Up, and it will begin down because it is odd. That graph goes exactly like that, from negative 3 to positive 1 to positive 5. If you wanted to, you could even mark the y-intercept. What is the y-intercept? 15. If you wanted to, you could. And just because I'm like this, I'm going to graph it on my calculator. X to the third. And what do we got? And by my estimation, I'm going to bring this all the way up to 80, just because I can. And my y values, or my x values, looks like I don't need all of these. I go back to -3, so I go back 2 more to -5. And from +5, I'll go over to +7. And we'll see how accurate of a graph I get. I mean, I don't know what your level of expectation is in life, but to me, that's pretty good. If you don't like it, try one more. I mean, that's, you know, there used to be a time where somebody showed that on your calculator, you thought it was magic. You're like, well, there's no way you could do that unless you had a calculator. Like, how would you ever do that without a calculator? You just do it. It's no big deal. You're the best. You're the smartest. You need an assignment.